point here is the tuning of the operating system. And basically what we do is that we have a script that is part of our measurement package, and it sets all the fancy IRQ stuff and thread pinning to CPUs, and sets the TCP/IP stack on the server that we are going to measure. So it's a good starting point for any other tuning of operating systems, actually. Then of course, the DNS server software that we are measuring is the key factor, or should be the focal point. And of course, dataset type affects the results, because we have, I think, 15 dataset types, which resembles, or we think that those datasets resembles the common uses of DNS, like it resembles operating, hosting server, or hosting a large number of zones, like 10,000 or 100,000 and 1 million of zones. But we have also a set that resembles ccTLD or root zone. Another factor is percentage of queries that actually asks for existing domain in the dataset compared to queries that ends up as NX domain answer. And of course, DNSSEC plays a key role here. There is some side thought, or there. Just to explain why do we do this, it's because in not DNS development, we would like to converge to sort of benchmark-driven development, which means that benchmarking should be a part of code review at some point. What we do now is slightly less than this. We usually benchmark key releases or major changes, and of course experimental features or experimental development methods. Like we have tried to compare different compilers or different compiler versions. We have tried to compare different settings for feedback-directed optimizations, like auto FDA in GCC. We also benchmark changes in internal data structures and methods for manipulating them, and we have put a lot of effort into benchmarking network interface cards. And I think that Ondřej presented the results on the last NanoC or something like that, which was really interesting stuff to do. Yeah. Okay. So what are our results? Usually we measure 10 points, like that. We send 100,000 queries per second, then 200,000 queries per second, etc., up to 1 million queries per second. And we have 10 points that represents how many queries returned back from the server. We can plot this as percentages, like on this chart. And as you can see, sometimes it's really obvious which version or which instance of DNS server is better than the another one. By the way, this chart shows impact of turning on socket option reuse port in GNOD DNS, which really helped a lot. And of course, the green line, or actually 3 green lines, represent 3 measurements randomly picked from set of measurements that was larger on the old version of NOT DNS without this feature, and the red lines are 3 measurements from newer NOT version, or newer NOT DNS version. But sometimes there are not so obvious situations like this measurement, and this is actually the comparison of the same not DNS version on two different operating systems. The first one is Linux, and the second one is FreeBSD. The red one is FreeBSD, and actually the reason for doing this was that we tried to assess whether it's better to run no DNS on Linux or FreeBSD, because we had some indications that on FreeBSD it could be actually better than on Linux. But trying to decide on this question, we came to point that we needed some more statistics. And we actually found out that the FreeBSD is much harder to tune, or actually it works like that. It's possible to hit some point of over-tuning, which makes the operating system unstable. So this was one problem, and another problem was that the measurements on FreeBSD showed more variance, and actually I have another chart for FreeBSD that shows the variance in our results. And as you can see, it's really hard to assess something about this server, or to decide what's better, because there is a huge variance on the right side of the graph. So actually, even though we were not able to draw some conclusion technically using statistics, I think that the administrators draw their own conclusions, and they are probably using Linux, or based on this, they would probably say that Linux is better for Node, but technically it's undecidable. And of course, there are really tough situations to decide on, like this one. This was another task for us, which was actually the comparison of compilers and settings of optimization in compilers. And we had three different binaries compiled by three different compilers with three different settings. It was red, green, and blue. And actually, you may see that it looks like that red is winning. But what we did was that in order to answer developers' question whether it's better to, or which compiler option is better to use, we tried to make the question more formal. So it's of course testing of a hypothesis, and we devised that a good test for this might be a Hotelling's test, which is sort of t-test, or it works similarly as t-test, but for vectors. So we have a vectors of groups of vectors that represents the measurements, and we are trying to decide whether the two groups have the same mean or same mean value vector, and which roughly represents whether the sets are the same. The drawback is that we need the groups to have, or the measurements to have same variance in both sets that we are trying to compare, which is not given, but we can prove it. And coming back to this figure, it actually showed that there is no statistical signal, or there is no difference that would be statistically significant among those three measurements, which was pretty interesting. But again, I think that developers decide for the red measurement or red settings anyway, because it looks better. And for more complicated situations, we have linear regression. This is basically the linear model. The idea was that to some point the response rate is linear in terms of sent queries, but there is a breakpoint when the server comes under pressure and it's saturated. So then the performance drops. Of course, it's not that dramatic like on this chart. It has a longer tail on the right side, but this is the idea, and this was the linear model. Actually, it's really beneficial to have some theoretical understanding into this, and it's really beneficial to have an LM because it's easy to fit, and actually we can use analysis of variance to find significant factors, which means that we can do a lot of measurements with different settings during operating system tuning or during development, and then we can use the ANOVA method to find which factors are helping us to get better performance. And another point is that having a lot of measurements or having more groups of measurements or having different groups of measurements, we can use Tarki HSD test or Tarki's HSD method to prove that some group is different from another, which means that we can prove that some solution or some version of the software is better than the another. Another method that we are thinking about and we are researching into that is pretty simple idea of estimating the breakpoint, which would produce a simple metric like that. If we estimate the breakpoint, we can say that the server performance is linear up to the breakpoint, and then it's dropping. But actually, one integer is quite a small amount of information, and it doesn't. What happens? Whatever. And it doesn't. It drops a lot of information from the LM. So, as I said, we are investigating this field now. And this is about the last addition to the testing suite. It was DNSSEC testing or DNSSEC benchmarking. We just tried to sign all our data sets and try to bounce packets over of the servers to see how does it work. And actually, it adds more variables or more factors, like the algorithm which affects packet length. Not that much, but there are some differences. And of course, NSEC or NSEC 3 is an important factor for DNS implementations. And another, from testing point of view, another factor or another variable was number of packets that actually, or number of queries that actually had the DO flag set to 1, which means that we usually send some mix of packets that are DNSSEC enabled and without DNSSEC, and it works in the same, or the idea is the same as with the packets or queries that we send to non-existing domains, just to test the system under real conditions. And actually, average response length was pretty high for us, or from our implementation, it was over 370 bytes, which limits the performance, or limits the theoretical performance to 3.3 million of answers per second, but we didn't hit that. Actually, the first measurement was pretty scary because it looked like this, and tweaked the system and our software and everything in the line, and after one iteration we get to this, which means that we optimized both NSEC and NSEC 3, or we optimized handling of NSEC and NSEC 3, which is now almost the same, but compared to blue line, which is the same test without DNSSEC, as you can see, there is quite a big gap among those measurements. And from what I have seen up today, nobody is, or actually all DNS implementations have some gap among the DNSSEC versus non-DNSSEC measurements. So it looks like that it's another piece of work or another homework for us to find some ways to optimize this. What are we going to do in future? We are thinking about adding more automation. Actually, we are thinking about using Ansible instead of shell scripts and instead of Python and all this stuff that we now use to interact among the measurement servers. We would like to add new data sets, especially for DNSSEC, and we are thinking about measuring DNS over TCP, which is quite tricky. So now it's in planning phase. We would also like to add comprehensive results to the website, and I would really like to spark a discussion about DNS measurement, because it's a really interesting topic, and we would like to hear some opinions about our methodology, both for acquiring data as well as processing them. And obvious idea is to use mailing list here in DNS OARC. So that's it. Thank you very much for your attention. And actually, if you would like to look at the results in easy-to-read form, which means that the results are processed and there are mean values from usually from sets of 10 or 20 measures, 10 or 20 measurements put into one line. So it's really easy to read. With all our data sets and all our measurement types, you can look at this website. If you have any questions, I would be glad to answer them.
Ray Bellis, ISC. Not a question so much as an observation. On your slide about variables, you're talking about NX domain proportion. One thing we've recently found with bind is that it's actually, particularly with authoritative zones with delegations, that it's far faster serving domains that are actually specifically in the zone that's being queried, rather than referrals that are below the zone cuts. Mm-hmm. So if you take, for example, the sample DNS per file, which has a whole load of random, fully qualified domain names rather than just the TLDs, then running that query file is a lot slower than if you ask specifically for example, com.dot or the glue that goes with com.dot that's in the root zone. We're talking tens, many tens of percent, if not even over 100% performance difference.
Okay, it's interesting information. I didn't know that, or so it's. I think that now we actually measure the first case, which means the referrals, and maybe we can create a data set that would reflect this feature. It would be nice.
And curiously, of course, that sort of query pattern is exactly what we might see in the future with QName minimization. So although we might see more queries as systems look for the zone cuts, the authoritative servers might actually specifically only then get queries for zones that are expected to be in the file rather than the referrals that are further down the path. Called QNames that are further below the delegation. So QName minimization may actually result in a higher effective throughput from our servers.
Okay, thanks for comment. Thanks.
Christian Petra, Stenik. Do you have a list of the compiler flags you have set for the benchmarking test with the red lines and green lines and blue lines?
Once more, do we have a list of what?
It's the compiler flags. Yes.
Oh, compile flags. Yeah, sure. Actually, the scripts that does the whole stuff are in Git, and the link is on the web page that contains the results. So you can download it and read through script, or you can post me an email, and I will pick the right line for you and send it.
Are there any recommendations which compiler is the best? Not the flags, the compiler, but because there's different compilers you have tested?
Actually, what I'm aware that we tried, because it was actually not my part. We tried GCC 4. Something, of course, and the C was the name for LVM, the compiler for LVM, which is C-lang, I believe. But I'm afraid that the results on website doesn't contain comparison of compilers. Maybe it's another point that we can add to the website.
Great, thank you.
Okay.
Ralph Nominum, to kind of basically ask further on this. You said a couple of times we increased the system like FreeBSD or Linux. We did something to it. Have you documented that somewhere?
Actually, as I said, we have a script that does the tuning, and the script is also part of the measurement package. So you can download it from Git and read through the script. It's
thanks.
Easy. Thanks.
Thank you. Next is Victoria Risk. She'll be talking about the impact of unknown eDNS0 options.
Can't even see that. Hi, I've got a lot of slides for 15 minutes, so I'm going to kind of race through it a little bit. I'm here to give an update on some work that Mark Andrews at ISC has been doing, measuring the impact of new eDNS options on the deployed authority servers out there. So first of all, the concern is that there are some new applications coming out that are introducing new eDNS options. Two examples are DNS cookies and the client subnet identifier. Bind has an experimental implementation of DNS cookies in the released version 9.10. That's been out for about 1.5 years. But in that version, the cookies are off by default. And cookies are only useful if they're widely available. So we would like to turn them on by default in the next major version, 9.11. I know. So Mark embarked on a little project to survey the DNS and find out what the impact was of new options. I have to say, I have to give credit for the graphic to Evan Hunt. I meant to put that on my slides. So you can read what it says there. Mark has been concerned for a while that even though eDNS is supposed to be a very forgiving protocol, you're supposed to be able to introduce new options without any negative impact, he suspected there would be a problem. So he's been running an experiment for about the past year. He's set up some dig queries that run continuously on 5 different groups of authoritative servers. You can read what the different groups are. If you look at his website, ednscomp.isc.org, he has all the details of what's in each query, what is the response he's expecting, and oftentimes there is an RFC reference there for why is this the expected response. So the headline is, there's widespread EDNS awareness. A lot of servers out there are EDNS aware, but when you look at the percentage of servers that basically succeed on all of the tests, the level is much lower. I'm only 2 minutes and 54 seconds in. So. Not too surprisingly, the level is the highest in the TLD and the root servers. Of course, they probably have been working on EDNS support because many of them have DNSSEC support. Whoops. So he's seen a lot of problems. This is a subset of the kind of errors or non-compliance with the RFC that he's seen. And you'll notice that some of these consist of queries being dropped or responses being blocked. And that whole category of things is probably due to overzealous firewalls. But there's another whole category, which is authoritative servers that are returning back the wrong response code. So I thought this was a great quote. I think it was from maybe the DNSOP mailing list, but it's really true. So part of the impact of this is it's slowing down the answers to the end users, and part of the impact is that resolvers are having to requery pointlessly, and that is antisocial. The bigger problem is, though, that some of the authorities, when they're presented with an unknown option, their response is to send back a form error. And this signals to the resolver that they don't have EDNS support and they retry without EDNS, which, if they're a validating resolver, means that they're unable to provide a valid response back to a client. So potentially, DNSSEC signed zones could become unavailable to clients that were behind validating resolvers. This particular chart comes from the .gov group. So he, one of the 5 groups that I said that he surveyed were .gov sites, and here we would expect that DNSSEC support is important. The green line that you see on the top it shows you a particular failure, which is responding form error to an unknown EDNS option. The good news is that this time chart shows over the past year, the incidence of that particular failure mode has decreased significantly. But this is the main concern that we have. Introducing more unknown options is going to cause some of the authoritative servers then to basically break DNSSEC. So I said I'd give an update on the trends since Mark started measuring this about a year ago. There's a lot of historical data on the website, ednscomp.isc.org. Most of these charts, if you mouse over them, you can see all the actual values. So I took a summary chart. These are the major problem types, and then across the bottom, they're grouped by TLD, the Alexa top 1000, the Alexa, I'm calling it the bottom 1000.gov and .au. We have the same thing for 2015. If you kind of go back and forth quickly, you can see there's some change. Since you can't really see that very well, I summarized it. On many of these measures, there's no real significant improvement, but it's not getting worse. On 4 out of 7 of these measures, we do have pretty significant improvement since last year. There's still an issue, but there has been some improvement. A lot of people are probably thinking, well, you know, what can I do about this? I just wanted to point out, we have multiple instances, if you look at the charts, where you can see that apparently a single operator has made a change that made a big difference. Here you see back on August 7th, there was an operator that had a firewall that was blocking EDNS, and they fixed the firewall, and it made a dramatic improvement in the results. This was somebody that Mark and I think maybe Ray contacted after seeing the results of the tests. One of the difficulties in loading the slides up ahead of time is just 2 days ago, 3 days ago on September 30th, somebody else made another change to their deployment. Some servers that were ignoring the EDNS version field were fixed, and that had a big impact. So the summary, why should you care about this? The first reason is it does result in slower resolution because of requeries. And of course, the resolvers are going to requery, especially when they think that actually the packet just got lost. These are, inefficient, slow. The biggest reason is the potential for causing breakage in DNSSEC. I will say, despite these figures, we haven't really seen user complaints or reports of problems coming from users. So I'd be very interested if anybody else thinks that they have seen evidence of this. It's possible that when people start having DNSSEC problems, maybe they attribute it to something else, I don't know. So what have we done so far? After running these tests for a while, Mark put up a self-test website, so you can go to that address and there is no www, just ednscomp.ic.org, and put in a domain and test it yourself. Mark has contacted a bunch of different operators who appear to have problems based on the testing, and some of them have made changes. The DNS Viz tool is also being updated to add checks for these EDNS compatibility issues. Mark gave a presentation at the IETF earlier this year, back in the spring, and now we're talking to here, and also Eddie Winstead is going to do a presentation at NANOG, trying to get people there to also test their sites. So what are we looking for? We're looking for people to test their own name servers, make sure that it handles version negotiation, make sure that it handles unknown EDNS options and handles unknown flags. And I just wanted to give a shout out. The folks at Switch actually started running tests on all of the domains in .ch and .li just to check those. And they have regular reporting also on their website showing the compatibility of all those name servers. In summary, we are planning right now to go ahead and turn on the DNS cookies by default, which will mean as people upgrade who are running bind, there will be more queries out there with EDNS options that will surprise some authoritative servers. And that's it. Any questions? Anybody seen any evidence of problems that could be attributed to this?
This is Stefan Lagerholm from Microsoft. Citrix NetScalers are dropping unknown options, or they're sending back form error. So, so that's a known bug. It's been reported to Citrix. Hopefully they'll fix it. But I think that also will give you a good bump in your statistics when they fix that.
Good, thank you. Okay.
All right, thank you. Next up will be Robert Edmonds. Left and right. Okay, that's slides.
All right, this is a presentation on some modern tools that may be useful for benchmarking and profiling DNS software. So I'm going to cover about a half dozen or so of these different low-level tools, use some of the output to generate drafts, and then take a more detailed look at individual hotspots that we might find in the graphs. This is a fairly basic hardware setup. It's basically the under my desk hardware spec. One big caveat is I only have 1 gigabit Ethernet, so I would just directly connected those links. And I've also disabled a bunch of power saving and hyper-threading features. This is the very latest Linux kernel. I've not made any attempts to tune it because it's 1 gigabit Ethernet. It should auto-tune itself. And I've taken the latest released versions of 3 production-grade open-source DNS servers, as well as a tool by Ray Bellis at ISC called DNS Echo, which basically just flips the QR bit and turns it into a response. So we got these individual tools. There's a toolkit called netsniff-ng, which is really interesting. It has a nice both packet capture and packet generation tools, as well as some statistical, or some the IFPPS tool, which records interface statistics. There's TC, or the Linux traffic control facility, something called mpstat, and something called perf events, which is a profiling facility offered by the Linux kernel. So trafgen is this user space traffic generator, and it's designed for performance and low-level flexibility. So it has a packet description language where you write out exactly what packet you want it to generate, and I found it was easily able to basically generate wire speed DNS queries from my dual core box. The downside is that you have to write the whole packet yourself, starting from the link layer headers. It does have a couple of useful macros. It has a DRND macro, which generates some randomized values, and it will you can tell it to calculate the IP checksum for you. In this particular case, I've written a packet that will generate the same question over and over again, but with randomized UDP source ports and DNS IDs, and with the EDNS section as well. This is just www.google.com type quad A. So I take that trafgen.cft file and I give it to this command line option, and it will send out as many packages as it can onto that interface. So the downside there is if I want to vary the query rate, I have to come up with some other way of doing that because it runs as fast as possible. For that, I used something called TC, which is a traffic control, traffic shaping facility that's been in the Linux kernel for about 10 or 15 years. And this magic command here will tell it to only allow X megabits per second out a particular interface. And for this set of benchmark runs, I basically had a script that would repeatedly invoke this command and ramp X from 25 to 750 megabits in 25 megabit increments. And the problem with this is that you tell it a particular bandwidth you want rather than number of packets per second. However, my packets are all the same length, so it ends up being a consistent packets per second rate. I've got some conversion, obviously do the division there, and the maximum 750 megabits in these benchmark runs translates into 1.1 million queries per second, which is almost, three quarters of a gigabit. There is a tool called IFPPS in the same toolkit. Basically, just get statistics from the network interface, low overhead. Has both a nice top-like interface, and it also generates CSV. There's an old tool called mpstat, which will record system load. And for these benchmark runs, I decided to take 100% minus the idle percent to get the overall system load. So that accounts for CPU consumed by user space, kernel interrupts, everything. So once that tool reports that the system is 0% idle, that's considered to be 100% loaded. For orchestration, I wrote a bunch of scripts that are not suitable for publishing that will start the server, start up the traffic control, start the traffic generator, and then ramp the traffic control over the specified range. Also record the packets per second and the system load for each increment, and then stop and shut down everything, and then repeat that for every single server. Here are the graphs that I made with the IFPPS and mpstat results. For this, I've just graphed responses per second against system load. So for this, we want a really nice linear line with low slope, evenly spaced points, and the breakpoint will show a cluster of points on the graph. Here's bind 9.10.3 configured with -- disable threads. It consumes, this is a quad core box, so it consumes all of 1/4 of the machine's CPU power. This is what you get when you enable threads, or when you don't disable threads. Notice it only consumes about half of the CPU. The problem there is the -U option, the command line option, is selected it auto-configures it suboptimally on this particular system. And here I told it to run listener tasks on all of the available CPUs, and this gets us up to the almost 100% CPU usage at around 400K responses. And then there's a cluster up at the top where it, the breakpoint basically. This is unbound with defaults. Unbound's problem is that it doesn't automatically detect the number of CPUs, so it starts one thread by default. If you tell it to run 4 threads and give it some additional tuning options, the graph looks like this, which is much better. We get almost 100, we get up to about 80% load or so. And then we start using more CPU, but not answering any more queries. This is the latest release version of Canot. It's basically a nearly perfect graph there. We go right up to 100% CPU, and we stay there at that maximum load. This is Ray Bellis's DNS Echo. It uses even less CPU than not, and so it looks like the problem here is I'm running into some scalability issues in the, either in the Ethernet driver or kernel or whatever, since we're not consuming all the available CPU or network bandwidth. Here's the best results for each piece of software on the same plot, and different colors, of course. So we have these 4 different servers performing differently, and we want to zoom in on one of these, one of these pieces of software, and profile it, see what's going on there. The Linux kernel has something called perf events. This is a bit easier to Google than just perf, which is the name of the command line tool. It's fairly lightweight, and it will give you insight into both the user space and kernel. This is used a lot in the Linux kernel community, but it's also usable for profiling user space programs as well. There's a perf top command line tool, which will give you a real-time top-like colorized interface, but instead of individual processes, it tells you which individual functions inside the individual processes are consuming the most CPU. And there's a number of other subcommands that will take a snapshot and report on it, and you can even take multiple snapshots of the same program and diff the results. It also has a additional feature where it can record call graph information, which means you can look at the whole stack basically when a in a particular, so instead of saying this function is consuming all of your CPU, what does the full program stack look like? You have to add this extra compiler option when you compile your program to get the best results from that. This command right here just runs a 3-second snapshot of the entire system and records the calligraph information. Then we can run this interactive tool to browse the profile that it then generates. This is what Bind's profile looks like at, I think, around, I think it was around 500 megabits or something. Then it starts up with with this tree collapsed, and then I've just gone and selected the part of the tree that has the most consumption. So it sorts it by utilization here, and I've just drilled down into the stack, and apparently this DNS name hash function is using lots of CPU, and then you can actually dig down into the annotated source code. This is source code interleaved with the machine instructions, and the numbers are, you know, percent of the samples within that function that where the sampler picked that, you know, the machine is executing that instruction. So that's some name hash function or something. That's about it. Are there any questions?
This is from the Jabber. This is from Marek at CZNIC. To Robert, is the trafgen still so slow when you generate queries algorithmically, i.e. functions in the config script? Pumping the same query isn't very realistic.
Could you repeat the question a bit louder?
Sure. Is the trafgen still so slow when you generate queries algorithmically, i.e. functions in the config script? Pumping the same query isn't very realistic.
Yeah, that's the big caveat with the traffic generator, is that I'm asking the identical question over and over again, so it's a 100% cache hit rate with a cache that only has one entry in it. So obviously that's either extremely optimal or extremely unoptimal, depending on your implementation. But I have experimented with the opposite of 100% hit rate, which is to randomly generate the entire queue name. I've not gone as far with that, but it seems that the limiting factor is not that the trafgen execution. It tends to, well, I probably need more CPUs in my sending system, but it tends to be pretty fast. I've not tried to give it like, you know, 1 million individual, because you can give trafgen multiple specifications, and it'll just execute each one in series. So I've not profiled that part of the system, so sorry.
Okay, you had a second question. Are you testing recursive or authoritative performance?
So for Unbound is recursive, of course. Bind, I tested recursive. I created a leaf zone with the exact record, and DNSSEC was just flips the QR bit.
Ray Bellis, ISC. Robert, did your network cards have multiple flow queues?
Multiple...
well, receive queues or transmit queues, because some modern cards, you can have them hash which CPU core packets are delivered to based on things like the IP address or even port numbers. And that can have an effect
so
on
my card
multi-threading.
does have that feature, but I decided not to mess with any kernel parameters for these sets of tests. But they may give you a few extra percent, but since it's 1 gigabit tests, I didn't want to bother with tuning kernel parameters. I wanted to focus on tuning parameters exposed by the servers themselves.
Right, okay. Yeah, and these are actually just network card parameters rather than kernel parameters as such. But, the I'm trying to remember the 10 gig cards I've been playing with have eight queues, and it makes a lot of difference whether you've got to hand over the packet from whichever core has picked up the packet to then whichever thread's then going to process that packet. So yeah, thanks.
Thank you. Next up is Joao Damas. We'll be talking about impact of DNS over TCP from a resolver's point of view. Left and right.
Hi, this is a bit of a study and a simulation of what would happen if you were to turn on TCP for every single query that is seen at a resolver or recursive server. Okay, so we'll go through the data sample. This is a study done using an actual one-day-long capture at a couple of the recursive servers at a medium-sized ISP. So this is what the query per second profile looks like on the external interface. So the recursive has a client stub-facing interface, and the interface where it queries the outside world. This is the traffic on the outside world. The cache for this server was running at around 84–85% effectiveness. So obviously, the traffic on the inside of the network is a lot higher. But this gives you a good sample, even if, of course, there are ISPs out there that have a lot higher load. So what's the cost? What would be the cost of just forgetting about UDP? In that sample, there are a few TCP questions, but very, very, very few. Most of the traffic goes over UDP, as it should. What would happen if you were to switch to using TCP for everything? So this is the traffic profile of the two servers converted to that. Of course, when you use TCP, you have an issue which you don't have with UDP, which is for how long does the connection, each individual connection, remain open after it's been done. The work it was asked to do is over, right? And that depends on several parameters, but one of the crucial ones is the closing timeout, the last timeout in the TCP stack. This influences not only how much state you are going to have to keep at any given time, but it also influences things that are perhaps going to surprise you if you don't think about it earlier, like port exhaustion. For instance, if you use the Linux kernel's default setup of using 60 seconds for TCP, the last stage of the TCP connection, before the port becomes available for reuse, you'll find out that once you get to like 1100 queries per second, you will run out of ports. There will simply be not be enough ports after 60 seconds of running in that mode to be able to issue a new query. So at that point, the server will just die. So we looked at what the thing would look like, which longer and smaller, shorter timeouts. A timeout of 5, which is the shortest we looked at, is actually something that you see people use out there very often on HTTP servers. Things like Nginx and high load web servers will reduce, for the same reasons that I was talking about, reduce their timeouts as much as they can to avoid keeping as much state as possible on the server side. And it mostly seems to work with today's networks, right? 5 seconds gives you time to receive an out-of-order packet that arrives after the FIN, a couple of times around the world, so it should be okay. So if you do that, then you see that the load is higher, but probably you can bear it. So one obvious way of reducing that load is if you see what would happen if you would allow connection reuse. So if you don't tear down the session, if you play with the timeout, what would be the chances and the consequences of, or how many queries can you fit into the same connection before it's closed? And unfortunately, the graph there, what it says is like most servers that this recursive server is querying out on the internet only get queried once during the validity of this timeout period. So basically, that's the 0 on the x-axis there, and it dominates the signal over everything else. However, there are connections that could use up to like 6 queries to fit into that exchange. On the other side, looking at things the other way, there are few servers that would clearly benefit from having an ongoing, probably permanent, forever connection. These, if we looked at which servers these were, and they were basically the servers that had to do with things like mail forwarding, that keep doing a lot of, this server does a lot of lookups for validating the emails towards the authoritative servers that have the recipient zones. So those servers would probably benefit from having a permanent connection, like a circuit almost established forever. But those are very few. This is for a few sample servers. What does their individual pattern of consultation look like throughout the duration of the sample throughout the day? And there is variety, of course. There are servers, like the one number 8 now on the purple line, basically are being queried all the time. But there are servers that are queried only during parts of the day. You see kind of interesting patterns. Number 1, for instance, you can probably deduct which part of the sample corresponds to the nighttime, because it just follows the sine curve, really, if you look at the density of the points. And then there are ones that are scattered. But if you look at those that have few queries, in a zoom, what you see is that on a very, very small time scale, so basically this is a few hundredths of a second that I'm zooming into, there's a lot of queries. So the DNS apparently goes in bursts. Probably because of retries, but also because of related queries. So those, for instance, would be being good candidates for making use of techniques like what Sarah was referring to earlier, like pipelining and repeated queries. So when we talk about using TCP, apart from the spook prevention, what other needs do we have? And one of the things that keeps coming up, I wanted to test whether it was true or how true it was, is the problem with the size and of the packets increasing, particularly with the deployment of DNSSEC, and whether eDNS is actually a valid mechanism to transport the extra bits when they go over the 512 bits effectively. So looking at that, this is the size distribution for all of the packets in that sample. As you can see, the overwhelming majority are small, like less than 500, and then you have a few other peaks. And then you have a long tail. This is actually not packet size, but DNS message size. So, for instance, in the small graph there, in the bottom corner, you'll see DNS messages that go to 8,000 and more bytes. And obviously, they will fall back to TCP even today, right? Interestingly enough, none of those huge messages actually have anything to do with DNSSEC. What you see, for instance, is hosting servers that actually seem to care enough about their customers that they set PTR records for every single one of them. But since the IP address is shared, you end up with an 8,000 byte long message of PTRs of all the customer names that share that IP address. I guess it's nice, but makes for some interesting messaging going on. Of the ones that actually return DNSSEC related data, and I must say that the servers running here, the 2 servers were running bind, so basically they will ask for everything with the do-bit set. So if there is any chance that anyone has any DNSSEC information in the domain you ask for, it will be returned. first thing that strikes me, and again, this is message size, not packet size, is that there is not a single message that involves the NSEC that exceeds 1,500 bytes. The curve is not cut off, it just ends up there. There is no message that's longer than that. So either people, when they run the NSEC, become very smart and care about things, or something else is going on. So if you look at the blue and the green graphs there, they will tell you when there's an X domain or no data answer, what is the size distribution, how does it vary when you use NSEC 3 versus NSEC. And it's true that there is a few more bytes that you can come across when you use NSEC 3. But actually, on the average, the NSEC 3 related messages tend to be shorter than the NSEC ones. And I couldn't quite understand why, because it's a bit counterintuitive. The other one, the black graph, is actually where there was actual information, and it's being returned and signed, not only the NSEC, which are also signed, of course. So looking at that, actually, size might not be the driving need for the usage of TCP over DNS. Perhaps if you want to avoid spoofing, then you should be looking at increasing the usage of things like the cookies, rather than massacring everyone else with TCP. Who knows? So basically, that's what we found. It would be good if the DNS had a bit more of a variety of signaling mechanisms. I think there would be a lot of information that about the behavior and negotiation that could go on between recursive and authoritative servers. But one of the things that DNS is sorely lacking is any sort of signaling mechanism. That's it for this study. Of course, there's the other side of the traffic, and we'll be looking at that soon, but we didn't have time to present it here. So that was a shorter talk. We'll have some more time. If anyone has any questions, happy to answer them.
Hi, Joao. It's Dwayne Wessels. I may have missed it at the start when you talked about the data source. Did that include both UDP and TCP queries already?
It did, but the amount of TCP queries that you were saying was very, very tiny. We're basically only using TCP for those extra long messages because most of the servers actually, when they had up to 1,500 responses, would actually use the UDP and the DNS for that. It's like Vicky showed earlier, actually a lot of people out there actually understand and respond decently to standard DNS.
Okay, thanks.
Hi, my name is Brian Summers. When you discovered that most servers dropped the TCP connection after one query, were you using pipelining, or were you waiting for the response before sending the next request?
This is, there's no pipelining in this simulation, because what we are doing is measuring the timeouts and the time gap between different queries. So we could perhaps see that if you were to establish a TCP connection, you'd perhaps compress. But if the next query is going to be 10 seconds in the future anyway, you would be wise to have closed that connection and not keep it around for that long. So basically what we're saying is, does the next query fall within the time within which you are willing to keep the connection open or not? And this time has to be short. Basically what was seen is that if you leave things to default and you don't care about actually conserving server resources, you will die.
Thanks.
Okay, I think that's it.
All right, we are running quickly. Next up is Mr. Fujiwara, who will be talking about DNS over quick. Left and right.
Hello, I'm Kazunori Fujiwara from JPRS. Today I will talk about just an idea, DNS over quick and zone transfer over quick or TLS TCP. This is my expectation for quick. I listened to quick presentations at ITF 93 Barboff, and TCP is weak to the man-in-the-middle attack. Anyone can terminate TCP connections by sending TCP reset packet. So any intermediate receiver can generate TCP reset packet. And interrupting zone transfer is very easy. And quick may solve the problem. Then I submit my abstract to this workshop. This is submitted abstract. And in that abstract, if possible, implementation status will be reported. But as a result, quick is complicated and I couldn't implement anything. So this is just an idea only. And this is quick abstract. Quick UDP internet connection, UDP-based secure and reliable transport for HTTP2 is developed by Google and Chromium.org. And specs are written in some documents. Draft TSVW Quick Protocol 01, Quick Loss Recovery 00, and Quick Crypto document. And currently, not well defined and many subscriber parts. And we need to refer current code at Chromium.org. And this is quick characteristics. Quick implements TCP plus TLS plus HTTP2 functions on UDP. And it doesn't require any changes in OS and network. And it is implemented as a library and user-land only. It's very important characteristics, I think. And one quick session can handle multiple streams. And each stream frame can be immediately dispatched to that stream on arrival. And any control and messages are authenticated and or encrypted. And Quick offers large connection ID 0 to 64 bit and large sequence number 64 bits. And it may be used as a cryptographic nonce. And I considered use case of DNS over quick. DNS over quick is equivalent to DNS over TLS, DTLS. And zone transfer over quick or TLS may help operation. And zone transfer over quick or TLS is, this is my idea of zone transfer over quick or TLS. Zone transfer is not encrypted, only authenticated by using TC or IP address configuration. Zone transfer over TLS may be required to protect zone contents from man-in-the-middle attacks. ACL may be changed to check certificates or their common names. And server configuration, certificate configuration may be added to server configuration, and zone transfer configuration, common name check may be added to zone transfer configuration, I think. And then I read quick specs, and after reading quick specs, in section 5.5 of Quick Protocol 01, there is a text, caveat, public reset packets that reset a connection are currently not authenticated. Attacker can generate a public reset packet, and my expectation was disappointed. and it will be fixed, I believe. And there is one open public implementation on www.chromium.org/quick, written by C++. And to build standard test server and client, it requires Chromium whole source tree, about 1.3 gigabyte, and requires special build system, Ninja, and limited information, limited documentation. We need to read the source code to understand any APIs now. So I'd like to test on another operating system. So I tested Quick on FreeBSD 0.1, and I found new port request for FreeBSD. Bug 202,286 new port net libquick devel, and tarball listed by destroying changed after the request. And I fixed destroying file and build the port. And the port requires huge tarballs, 372 megabyte. And the build, this port worked well. And it can compile libquick library and test server client. And result of building libquick showed that there is a huge library, 138 megabyte libquick.so.0 and many header files, 933 files in user local include Quick, and normal size binaries, Quick simple client and Quick simple server. And to run the Quick, I checked smallest compile command for a client, and C++ with some options and some C++ files, and it requires non-installed header files 22 and I read main part of the client. Main part of client are composed of client initialize, connect, and send request and wait for response function. As a result, blocking code may be easy. And I checked Quick simple server. This is a small compile command for a server. It requires 10 or 12, 13 C++ files and some compile options. And the main part of the server contains server class and server.listen and base : run loop.run. And the main loop may be in Quick library. It is similar to boost ASIO and review event. And we need to integrate, if DNS server, to make DNS, to add Quick function to existing DNS server, we need C++ DNS server implementations. Bandy or Power DNS are written in C++. And there is a port 53 UDP problem. Port 53 UDP may be shared with both DNS over UDP and DNS over Quick. And Quick can handle address port change, but I'd like to ignore the function. And the client knows the response packet type. When client sends packet by UDP, then response must be DNS over UDP, and when client send DNS over quick, response must be quick. And server need to accept both DNS over UDP and quick and DNS over TCP. And servers need to determine that received packet is DNS over quick or DNS over UDP at DNS query receiver. And I considered how to determine DNS or DNS quick. Basic idea is that pass it as DNS over UDP or quick. If errors occur, it's another protocol packet. And if quick connection established, records the combination of source destination address port pair. And this is my idea. And if source destination address port combination is established quick connection case, it's quick. And if the packet doesn't seem to be DNS over UDP, try quick, it's heuristic. And another case, pass received packet as DNS over UDP and it passed as a form error. It's quick packet. And this pseudocode may be such code. Initialize and create socket, and then event loop, and if packet received from, and quick test, and established quick test, and heuristic DNS check, and DNS pass as a DNS. This is final slide. This is current status of DNS over quick. The current quick specification is unsatisfactory and incomplete, I think. And implementation exists, but too complicated. And do you know simpler quick implementation written by C? If possible, I'd like to integrate DNS server written by C++ and live quick. And that's all.
Hi, this is Shane Kerr from BII. This is an interesting presentation. I was especially pleased to see Bundy mentioned. So if the main motivation is to avoid TCP resets, did you consider looking at normal IPsec tunnels to avoid this problem?
Yes, IPsec or VPN can be a good solution.
Okay.
But in many cases, users doesn't use NAT. Many people doesn't use VPN or IPsec to transfer zone transfer, to use the zone transfer.
I guess I was just thinking that in terms of the administrative overhead of setting up, it's not really different from the exchange for a TSIG setup, and then you get a encrypted and reset resistant connection. Anyway, so thank you.
Thank you.
Randy Bush, IJ Fujiwara-san. The most disturbing thing was the fact that you found the spec being discussed in TSVWG to be insufficient. Will you be in TSVWG in Yokohama, and have you scheduled to make a presentation of what you found lacking? What you want fixed? Because if I've met you before, if you found it lacking, I am very worried.
Thank you.
Jeff Houston, APNIC. This is possibly a question to Google, but it's easily also a question to you. One of the most prevalent things in today's internet is, of course, NATs. And one of the more interesting things about NATs and TCP is that the TCP session tells the NAT when to create and release bindings, because the SYNs and the FINs basically inform the NAT what it's doing. UDP sessions are always a bit of a kind of shot in the dark with NATs, because the NAT has no idea when and how to release the binding. So what behaviours do you think are appropriate to make this kind of thing resilient if you happen to be stuck behind a NAT? Or are you just hoping that Google's somehow solved it with Google magic?
Pardon?
Quick is UDP as well, so I'm saying Google has exactly the same problem as I'm asking here. You know, it's not that there's an easy answer, but I'm saying once you go into a UDP-based mechanism and you're faced with NATs, what's plan B when the NAT drops your binding? Because there's no explicit signalling left to say to the NAT, keep going because I'm still active. Because he's doing long-held transfers versus single transactions. That's what I thought.
Between clients, it's solved by quick, and network operator cannot handle, I think.
So you're saying it's kind of whatever Google's doing will be good enough for you? Okay.
So I'm not sure if you can answer this from the work you've done so far, but hold on. I'm not sure you can answer this from the work you've done so far, but I'm intrigued to know if you got a feeling for, in terms of server resources, where Quick sits in the spectrum from UDP to TCP to TLS and DTLS, in terms of the memory requirements and also CPU.
CP's memory.
Compared to doing standard UDP or TCP?
Quick takes many memory and CPU, I think, but it's end host, and CP's usage is not changed, I think. CP is not table size. Not table size may not change, I think.
But because it still requires more state than UDP, then it's consuming more memory. Is that correct?
I don't know now.
Okay. Thanks.
Michael Sinatra, ESNet. I may be reading the Quick wrong, or the motivation for Quick wrong, but it feels to me like it's kind of to some extent, sort of a statement that we're kind of giving up on SCTP ever happening. And I just wondered what the thoughts of the audience, this isn't necessarily a question for you, but what the thoughts of the audience were on DNS over SCTP, and if that's still going to happen, or if anyone thinks that's ever going to happen.
Thank you.
Just a quick comment on that, Dave Lawrence, Akamai. Personally, I'm in favor of it. How far has that gotten us? This is a significant issue, of course, that's being undertaken in the IETF right now, looking at the transport layer and how we can have actual transport innovation rather than trying to, say, force everything over HTTP, as is being done by many protocols in development now. If you are interested in being able to push forward things like SCTP, you should get involved in the TAPS working group and the rest of the transport area in the IETF.
Thank you.
And the BOF on Monday, what's that one called? So there's a research group also on Monday morning at the BOF that starts with an H, HOPS. So to answer the question, though, regardless of whether we've given up on SCTP, and I think that maybe Fujiwara-san, you've missed the reason why the Quick document was published at all. I mean, Quick really was designed to work over TCP, but it had some ideas that if you squinted hard might be able to be pushed into UDP. And really, as far as I understand from talking to one of the authors, that the main reason why they've published it at all is not because they expect it to be adopted as is, but it might be adopted as part of some of the work that will be coming in the what do we do if we have UDP and such. And that's, by the way, just of course, a huge political mess in the IETF because some people very much want this, some people don't want it at all, some people only want it after we've gotten security, but it's being designed without the security first because what's more important is, can we even do this? Quick is somewhere in the middle, so they wanted to publish it, but I don't think they expected anyone to actually try to implement it. As you found when you were doing it, it's not like that there's a simple implementation of it. So this may be premature at this point, and later on we might find good reason for it. We might not.
This is Allison Mankin. I just wanted to add something that is very clear from the Quick BOF at IETF. Quick is 100% encrypted. It's the advanced guard for HTTPS everywhere. And in fact, TLS 1.3 and Quick are very similar. And right now it runs on port 443 on UDP when Google runs it, as I understood. And I just looked at the facts. So it actually has a lot of the qualities and it's connection-oriented too. So I think there's some really interesting questions to ask about what happens as it moves along, as it starts to be used by others of the platforms, whether it's actually going to go to standardization so that you would be able to use it in a kind of an open way, and then what does it mean for something like DNS with our multiple protocols? Could we all converge on one protocol? Could it meet some of our requirements? But I agree with Paul. It's kind of early for anything other than really experimentation.
I would only like to use existing good protocol. Thank you.
Thank you. That was the last presenter for this session. I'd like to thank everyone for their presentations. And then I'd like to hand it over to Keith, who will be wrapping this up.
Okay, thank you, Liam. Thank you to all our speakers this afternoon, particularly for finishing on time. There's just a few short announcements between you and beer. We've had one or two minor issues with the network. There has been some outgoing lag, which the Nano guys have been trying to diagnose, and they think they've got a fix, but they're going to shut the network down sometime between 6 and 9 to try and address that. There was a problem with 8021X. That should have been fixed for the past hour. Is anyone still having trouble using the 8021X SSID? Okay. I think there's probably still some T-shirts outside, so please collect your T-shirt if you don't have one, and save the Sierra guys from having to carry them back. For the social, there are directions on the Indico site for the meeting. As I say, it's not the closest venue, but it does let you see the city a little bit more than just the downtown area. If you're walking it, the best thing to do is to go out the front entrance of the hotel, cross René Lévesque Boulevard, and then basically go north briefly for a sort of large block until you get to Rue Sainte-Catherine, and then basically you need to head east for about a kilometre. When you get to Saint-Dominique, you need to turn right. It's kind of down an alleyway, but it will be obvious from the security guy and the rope that that's where you need to go in. When you get there, make sure you have your badge. When you verify your badge, you will get tickets for drinks. There's then an elevator up to the 5th floor. It's a nice roof deck. Hopefully the weather will actually be up to spending a little bit of time out there. So a big thank you to Sierra for being our social sponsor as well as our gold sponsor for today and the T-shirts. And also, thank you to Nominum for being our bronze sponsor today. If you got a blue voting card for the AGM, it would be helpful if you could just hand that back to the registration desk rather than leave them lying around. If you're leaving at some point, it would be great if you could return the badge lanyards and holders, but I hope that after today's program that you'll be staying for all of tomorrow's program. You'll also notice in Indico that there is also an analog DNS track. That is basically a repeat of some of the material for this workshop. We work closely with an analog program committee. So that's happening on Monday afternoon. You need to be registered for NANOG to go to that. I hope a lot of you are going to NANOG, but essentially it's similar material. There's a little bit of new material in there, so just in case anyone's wondering about that. And basically, what time do we start again tomorrow, Sebastian? 9 a.m. tomorrow, so go easy on the cocktails tonight. Thank you to everyone today, and I'll see you at the social and tomorrow morning.